This lecture concerns iron making. Is typical example of application of reduction smelting unit processes, as I have given you in earlier lectures. Now, the objective of this lecture is material balance in iron making. Now, before I go straight away into the material balance, I thought it to be appropriate to give you a little bit of conceptual part of the iron making, so that you are prepared for material balance and heat balance problem in iron making. Now, as all of you know, the reactor in which iron is made is called blast furnace. So, as such, this is the blast furnace iron making. And on my left, this is the sketch which I have drawn for blast furnace. I will come to that. Now, typically what is done in iron making, now I will again tell that my objective of this lecture is not to give you all aspects of iron making, but I will be giving that portion which is relevant for performing material and heat balance operation. So, in iron making, in fact, iron ore concentrate plus coke plus flux plus air results in hot metal plus slag and plus gases. A mixture of, say, iron ore concentrate which is typically used in the form of sinter or pellets, plus coke plus flux. This mixture is called burden. The role of flux is to slag the impurities. That is, flux is added, and mostly the flux is limestone that is added. And limestone, it decomposes to calcium oxide and CO2, and this calcium oxide reacts with the gangue minerals of the ore, that is SiO2, Al2O3 and so on, and helps in producing a slag. Coke is a principal source of thermal energy, and as well as chemical energy. As in the previous lecture on coke making, I have detailed what is coke making and so on. So, the carbon of the coke, it acts as a reductant for reduction of Fe2O3 to iron. The combustion of carbon of coke, it also provides a thermal energy. So, in fact, coke is a source of thermal and chemical energy. Now, let us come down to this charging sequence and how it is done. So, the burden is charged from the top, the burden is charged from the top, and this portion is called stack. This portion is called belly. This portion is wash, and this portion is hearth. And hearth, it has a tape hole for hot discharge of hot metal. Hot metal is heavier, and on the top you have the slag. It has a tape hole for slag and hot metal. So, the hot blast air This is hot blast air. This is also hot blast air. Hot blast air. That means, the hot blast air is introduced through the tuyer which are located at the periphery of the blast furnace. Now, what happens? As the burden descends, so the direction of burden descent is downward, whereas the gases travel upward. This is the gases and this is the burden. So, from conceptual point of view, blast furnace, I will denote by BF, is a counter current, heat and mass exchange reactor. Needless to mention that in any counter current heat and mass exchange reactor which consists of gas and solid, the permeability of the bed, the distribution of the burden is a very important issue. For the smooth operation of the blast furnace, the upward rising gases should travel unhindered, as well as they should transfer their heat and mass to the descending burden. The transfer of mass I mean by way of reaction of carbon with the oxygen of Fe2O3, that is what. So, needless to mention about the importance of burden distribution, that all constitutes a portion of iron making when once we go into the detail, but as regard material balancing is concerned, we rather take it for granted that the gases, there is a smooth movement of burden and gases. So, sometimes what is being done through the tuyer of the blast furnace, sometimes the oxygen enrichment, hydrocarbon injection, is also done. So, as the burden descends, the gases travel up, the reaction between Fe2O3 and carbon of coke or carbon monoxide which is forming due to the reaction, the iron oxide gets reduced. So, as the burden descends, the carbon of the coke reacts at the tuyer level. So, carbon of coke, it reacts with O2 at tuyer level, because it is here oxygen is available. So, what happens? C plus O2 plus 3.76 N2, that is the 1 mole of air, immediately it forms CO2 plus 3.76 N2, and this CO2 plus 3.76 N2 in presence of excess carbon, it forms 2CO plus 3.76 N2. So, the upward gas rising consists of CO plus nitrogen and plus carbon monoxide. Now, as a result of reaction of carbon of coke with oxygen at the tuyer level, a temperature approximately around 1900 degrees Celsius to 2100 degrees Celsius is created. Now, as the gases move and they discharge from the top of the furnace, the exit temperature of the gas, is approximately somewhere between 200 to 250 degrees Celsius. So, you can imagine how efficient the blast furnace is from the point of view of transfer of heat. So, the exit temperature of gas is around 200 to 250 degrees Celsius. As the gas is rising upward, what happens? The reaction between say Fe2O3, say 3 Fe2O3 plus CO, it gives you 2 Fe3O4 plus CO2, then Fe3O4 plus CO, that gives you 3 FeO plus CO2, then FeO plus CO, it gives you Fe plus CO2, and this reaction CO2 plus C, it gives you 2CO. So, these reactions are happening as a result of heat and mass exchange between the upward rising gas and downward movement of the burden. Now, one important thing to note, these reaction and this reaction, they do not require very high percentage of carbon monoxide. So, they can occur towards the upper region of the stack, whereas the reaction FeO plus CO is equal to Fe plus CO2. Now, this particular reaction it requires high concentration of CO, and at around 900 degrees Celsius, the equilibrium concentration of CO in CO-CO2 mixture should be around 65 to 70% for FeO to be able to reduce to iron. So, particularly this reaction FeO plus CO is equal to Fe plus CO2, it occurs at the point of stack and Bosch region where you have high concentration of CO. So, that is an important thing. Now, in the reduction process, some iron oxide is also reduced by carbon, and this reduction is called in fact direct reduction. This is endothermic in nature, whereas all these reactions they are called indirect reduction. So, in the blast furnace both indirect as the direct reduction are going on, and attempt is made such that the heat balance is there at every region of the blast furnace. So, some of the say oxides, say for example, SiO2, MnO, P2O5 and FeO. Say some of the oxides they are reduced by carbon and they form silicon plus 2CO, MnO plus C, it forms Mn plus CO, because they all take place at very high temperature. P2O5 plus 5C, that gives you 2P plus 5CO, FeO plus C, that gives you Fe plus CO. So, all these reactions they occur between the belly and the Bosch region, the temperature being very high, iron gets melted and it absorbs silicon, manganese, phosphorus and sulfur is present, and thereby the formation of hot metal takes place and hot metal trickles down. So, hot metal is a molten mixture of iron plus carbon plus silicon plus manganese plus phosphorus plus sulfur. Carbon is also absorbed because carbon is present over there. So, this hot metal formation is accompanied by the formation of slag. So, slag is also formed such that the gangue minerals are separated. So, slag typically consists of say CaO, SiO2, then MnO, then Al2O3. That means, all other impurities of iron ore, it gets eliminated near the Bosch region and all are in the fluid state, and both hot metal and slag, it trickles down into the hearth region and because of the density difference, the hot metal and slag are separated. So, that is how in short the iron making in blast furnace is there. Now, here some of the important point to note that most of phosphorus, in fact all phosphorus, it enters into hot metal, Now, this typically because blast furnace iron making is under highly reducing condition. So, therefore, all P2O5 of the ore gets reduced to phosphorus and all phosphorus enter into the hot metal. Now, in this process of iron making, though the conditions are highly reducing, even then some amount of iron is oxidized. So, as a result slag in addition to CaO, SiO2, MnO and Al2O3, it also contains some amount of FeO. However, the FeO content is very less because of very high reducing condition, hardly 1% or 1.5% of FeO you may find in the slag. Now, about the exit gas. The exit gas typically consists of CO, CO2 and nitrogen. So, that is in short the blast furnace iron making is a burden descends downward, it comes in contact with the upward gases or upward mixture of gases. As a result of heat and mass transfer, iron oxide gets reduced to iron, the gangue minerals are slagged or all fluxed, nearby belly and Bosch region iron melts, it absorbs surrounding carbon, silicon, manganese, phosphorus and hot metal forms, and by virtue of the density difference between hot metal and slag, both are separated and hot metal and slag are tapped. So, this is what from the material balance point of view I presented very brief overview of the iron making. Now, let us see now the material balance in iron making. Now, say for calculation purpose, we make macroscopic balance. Macroscopic material and heat balance. Now, by the term macroscopic material and heat balance, it is meant that we are concerned only at the inputs and outputs. That means, here we are concerned only with the inputs and outputs. In between, what is happening? It does not come into the purview of the macroscopic balance. So, what is interested or what we want is a macroscopic material balance, where we are concerned with the inputs and outputs. Now, we are here, what will be our objective of this calculation? Say first we will like to calculate charge balance, for example, charge balance. Now, charge balance we would like to know, say if I again draw a material balance type of box. So, this is my reactor. So, here my inputs and here I have outputs. Now, in the blast furnace iron making, the input consists of iron ore, of which the composition should be known. Also, input consists of coke, of which composition should be known. So, iron ore, it can have Fe2O3, SiO2, Al2O3 and so on. Coke, it can have carbon, you should also know SiO2 and what other composition. So, their amount and composition should be known. third input is limestone. So, limestone, what is the composition? Say amount of SiO2, CaCO3, Al2O3 and what are the composition and amount. And also input consists of air, its amount. So, of this input side the important is amount and composition. So, in a macroscopic balance we are only concerned at the inputs. On the output side, the output consists of, for example, you have hot metal. Hot metal composition, say iron, carbon, sulfur, silicon, manganese, phosphorus. So, here again composition and amount we are interested in. Then another output is slag. Again we are interested in composition and amount. Composition and amount. Third output is gases. It may consist of CO, CO2, N2, composition and amount. So, when we say charge balance, that means we should know for a given output, now whichever way the problem can be formulated. For a given output, what should be the input? For a given input, what should be the output when sufficient number of variables are given. Now, what can be done here? In order to calculate also macroscopic heat balance, in addition to the amount, the important is the temperature at which the inputs are made into the furnace and temperature of discharge, that is also important to know. So, when we want to do the heat balance, then we should know temperature of all inputs. Should know temperatures of all inputs, air, limestone, coke and iron ore. Unless we know their temperatures, we cannot calculate the heat balance. Then here in the output side, that we should also know the temperature of all outputs. Temperature of all outputs, it must be known. In addition, you should also know some of the thermodynamic data. Some of the thermodynamic data. Say heat of reaction, Cp value and so on, whatever is needed. So, this is in short the charge balance. When we say charge balance, that is what is meant by charge balance. Now, when we talk of the heat balance, when we talk of heat balance, then we must know all heat input sources, all sources through which heat is input, then all sources through which heat is out. The objective is to calculate heat deficit, or also you would like to calculate what is the thermal efficiency of the process. That is how the scheme of charge balance and heat balance looks. Now, say let me illustrate a charge balance by taking a suitable example. So, in an example, let me take an example to illustrate. So, let me take, this is the reactor. Say I am charging here iron ore, whose composition is Fe2O3 78%, SiO2 8.4%, MnO 0.6%, Al2O3 5.0%, P2O5 1.7%, MgO 1.2% and H2O 5.1%. Then flux is charged and flux amount is 1/4 weight of ore. Flux, its amount is 1/4 of the weight of ore and it is the composition is CaCO3, MgCO3 and SiO2. This is 96, this is 2 and SiO2 is 2. Then coke, coke is charged and coke is charged 900 kg per ton of hot metal. 900 kg per ton of hot metal. Composition carbon 88%, SiO2 9%, Al2O3 1% and H2O that is equal to 2%. This is all the output, input. Now, on the output side we have hot metal and hot metal composition, it contains iron, carbon, silicon, phosphorus, silicon, phosphorus and manganese. So, iron is 92.7%, carbon 4%, silicon 2%, phosphorus 0.9% and manganese 0.4%. Gases, CO is to CO2 in this particular problem, that is equal to 2:1. Also it is said that 99.5% of iron is reduced. That means, only 0.5% of iron is slagged. So, we have to make now calculations. Now, first we have to calculate weight of ore. Weight of ore. Now, for that we will be making iron balance. We have to do iron balance, that is the first thing that we have to do it. Now, first we select the basis. So, basis is 1000 kg, basis is 1000 kg hot metal. Now, if we make iron balance, so we have noted in the problem that 99.5% of iron in iron ore, that is equal to iron in hot metal. This is 99.5% of iron in iron ore. So, if you do this calculation, because remember all iron you have to see the source of input and source of output. Now, in this particular problem iron is entering from iron ore and it is output iron in hot metal and iron in slag, but it is given 99.5% is reduced. So, our life becomes easier. So, we straight away go 99.5 upon 100 into 112 upon 160 into 0.78 x, that is equal to 927, where x is the kg ore. So, then x that is equal to 1706 kg. So, this is the amount of iron ore. So, what I wish to say is that if you want to calculate the amount of iron ore, the iron balance is the starting point. Now, the next slag is not given. So, we have to calculate weight of slag made. We have to calculate weight of slag made. Now, here the concept is important. The slag will consist of, if you see the analysis which is given in the problem, the slag will consist of SiO2, Al2O3, MnO, P2O5, MgO, calcium oxide and so on. We have to calculate now the weight of each constituent of the slag by making the elemental balance. So, let us first of all do silicon balance. Let us perform silicon balance. So, silicon balance, that is silicon in ore plus silicon in coke, amount of coke is given to us, plus silicon in limestone, amount of limestone is also given, that will be equal to silicon in hot metal plus silicon in slag. Well, choice is yours, you can do SiO2 balance or silicon, it does not matter at all. So, if you do this particular balance, now all that we have to put, say for example, silicon in ore, that is 1706 into 0.084 into 28 by 60, that is silicon in ore, silicon in coke 0.09 into 900 into 28 upon 60 plus 1706 upon 4 into 0.02 into 28 by 60, because limestone is 1/4 of the weight of the ore, that will be equal to 20 silicon in hot metal and plus silicon in slag, that is what we want to find out. So, if we perform this calculation, we get silicon in slag, that will be equal to 88.65 kg. Therefore, SiO2 in slag, that will be equal to 88.65 into 80 upon 28. Do not forget to convert Si to SiO2, because remember slag consists of oxides, it does not contain any elemental. We have done elemental balance because we want to do, because of our convenience. You may do SiO2 balance. Hot metal, it does not contain any oxide, it contains only elemental form of the element. So, that is an important thing. So, that calculation gives you SiO2 in slag 189.97 kg. This is about the SiO2 in slag. So, in calculating each say component of slag, we have to do the balance. Now, similarly we can do say Al2O3 in slag, Al2O3 in slag. Now, fortunately here all SiO2 from charge from all sources, it enters into slag. So, Al2O3 in slag. So, we can directly do the Al2O3 balance. So, Al2O3 in slag, that will be equal to 0.05 into 1706, that is Al2O3 from iron ore, plus 0.01 into 900, that is Al2O3 in coke. So, that forms 85.3 plus 9. So, Al2O3 in slag is 94.3 kg. Now, a bit patience and bit say overall look of the problem is necessary. You should know from all sources. As my experience said that some while doing very fast calculation, you may forget one of the source. Say for example, Al2O3 coming from coke is only 1%, you may forget this 1%, then the answer becomes wrong. So, here patience and the overall brick of the problem is required, so that you know from which sources what is entering and you take into account. If you can do that, there is no problem in doing material balance. Now, similarly, MNO in slag, find out MNO in slag. MNO in slag. Again, you have to do from all sources input and output. So, MNO in ore, that will be equal to manganese from ore minus manganese in pig iron or manganese in hot metal. You may call pig iron also, it does not matter. Now, this is the balance will go into the slag in the form of MNO. So, we have to convert it into 71 upon 55. Now, the molecular weight of manganese that I have taken 55, or oxygen as usual 16, silicon 28, iron 56. So, if you substitute all the value, so manganese from iron ore, that will be equal to say 0.6 into 1706 into 55 upon 100 into 71 minus 4, that will be into 71 point upon 55, and that makes approximately around 5.1 kg. You get 5.08 or something. So, 5.1 kg it makes. So, that is how you will calculate the MNO in slag. Now, gradually we are building the amount of slag. So, ultimately the amount of slag will be the sum total of all that we have calculated. Similarly, we have to calculate P2O5 in slag. P2O5 in slag, that will be again equal to phosphorus from iron ore minus phosphorus in hot metal multiplied by 142 upon 62. The molecular weight of phosphorus is 31. So, we do this from iron ore 1.7 upon 100 into 1706 into 62 upon 142 minus 9 multiplied by 142 upon 62. So, this will be equal to 8.4 kg. This is the amount of P2O5 in slag. Now, similarly, we have to calculate MgO in slag. MgO in slag, because MgO is entering through iron ore. So, all MgO will enter into the slag. So, MgO in slag, that will be equal to MgO in iron ore plus there is another source of MgO, that is MgO from flux. So, these are the important things, all sources to be known. Now, MgO in iron ore plus MgO from flux, because MgCO3, say the flux contain what? It contains MgCO3. So, MgCO3 will decompose to MgO plus CO2. So, this MgO will enter into the slag. So, MgO in slag, that will MgO in iron ore, that will be 1.2 into 1706 upon 100 plus 1706 upon 4 into 2 by 100 into 1 upon 84 into 40. So, that is equal to 24.53 kg. Now, here the atomic weight of magnesium is 24. So, we got now we have to calculate calcium oxide in slag. Calcium oxide in slag. Now, it is very simple, the source is only calcium carbonate. So, if you calculate, it will come 229 kg. Now, the problem also says 0.5% of iron is slagged off. So, there will be FeO in slag that will be equal to 0.78 into 1706 into 112 upon 160 into 0.005 into 72 upon 56. So, that is equal to 6 kg. Now, with this calculation, what message I want to give, that in this particular problem you have to do the elemental balance or oxide balance, whichever way is convenient to you, in order to get the amount of total amount of slag. The most important thing is to see that you include all sources from where a particular element is in and all sources from where it is out. Now, to summarize, the amount of slag, say slag, the components are, say we have SiO2, we have FeO, we have Al2O3, MnO, P2O5, MgO and calcium oxide. This is what the components are. So, their respective weights in kg 189.97, FeO 6.00, Al2O3 94.30, MnO 5.10, P2O5 8.40, MgO 24.53 and calcium oxide is 229.00. So, that total it will give you around 557.3 kg. So, in percent, if you are in, we can calculate, that will be 34.09, 1.08, 16.92, 0.90, 1.50, 4.40 and calcium oxide is 41.10. If you are interested, you can also calculate the basicity of slag, that is percent CaO upon percent SiO2. So, that will be 41.10 upon 34.09, that will be approximately 1.2 around that basicity of that slag. So, this also can be done. So, this is about how to calculate the volume of slag. Now, next thing we have to calculate volume of air required. Volume of air required. Now, you require air to combust carbon of coke. So, amount of air is important. Now, in order to calculate the amount of air, you have to subtract the amount of oxygen which is available in the charge. Now, here that means you have to consider, say, oxygen available from the charge. To consider oxygen available from the charge. Because SiO2 it is reduced with carbon, you have silicon. That means, some amount of carbon has already reacted with the oxygen of SiO2. So, that much amount of oxygen which is available from the charge will not be supplied by air. So, in order to calculate the volume of air, it is necessary to calculate the oxygen available from the charge, and then the oxygen from air in order to calculate oxygen from the air, you should know how much oxygen is available from the charge. So, for that, say you are in this problem, oxygen from CaCO3 will be available, oxygen from MgCO3 will be available, then O2 from SiO2 reduction, because silicon is forming and silicon is entering into metal, then oxygen from reduction of MnO, then oxygen from reduction of P2O5, then oxygen from Fe2O3, and that will be equal to O2 of Fe2O3 minus O2 of FeO in slag. So, that is how all these calculation has to be made, and then if we do that, for example, oxygen from CaCO3, I think you can calculate these things, and if we do that, total oxygen available from charge, oxygen available from charge in this problem, it comes around 17.742 kg moles. That much is the amount of oxygen available from the charge. Now, in order to calculate amount of air, we have to find out total carbon in gases. Total carbon in gases. Now, total carbon in gases, that will be equal to 0.88 into 900 upon 12 plus 0.96 upon 100 plus 0.02 upon 84. This is carbon from CaCO3, is from MgCO3 into 1706 upon 4 and minus 40 upon 12, that is carbon in pig iron. So, we get the total carbon in gases, it comes around 66.863 kg moles. Total carbon in gases, it comes around 66.863 kg moles. Now, CO-CO2 ratio is given 2:1. So, C to CO, that will be equal to 44.575 kg moles, and C to CO2, that will be equal to 22.288 kg moles. Then here we find out O2 required for 44.575 moles of CO, that will be equal to 22.2875, and O2 required to form CO2, well, C plus O2 CO2, 22.288. So, total amount of oxygen that you require to supply is 44.5755. Remember, this oxygen is available at the tuer for the carbon to combust. So, O2 from air, that would be 44.5755 minus the one which is available from the charge, we have calculated 17.742, that will be equal to 26.833 335 kg moles. So, therefore, amount of air that will be 2862.24 meter cube. That is how you will be calculating the amount of air. Now, the last thing which is left is the volume and percentage composition of blast furnace gas. So, in order to calculate volume of gas, we already calculated CO, CO2, all that we have to calculate nitrogen. So, if you do and we have to add H2O. So, volume of gas that will be equal to 172.642 kg moles. So, that makes the calculation of charge balance complete.